Hey there, welcome to Galileo's AP STEM. Today we are covering topic 2.3 of the AP Chemistry curriculum, so if your mind is ready to synthesize, then let's learn the structure of ionic solids. But first up, we gotta refresh your mind on what exactly an ionic bond is. And if you've got good memory, then you would know that an ionic bond is an electrostatic attraction between a cation and an anion. Now, sure you know the definition, but what exactly makes a cation attract to an anion? Well, to answer that question, you have to understand that a cation is a positively charged atom and an anion is negative. And as we know, particles want to reach equilibrium and make that charge zero. So when a cation with not enough electrons and an anion with too many electrons see each other, the anion will give away its electron and the cation will receive it, and boom, they're both at equilibrium. Now that you understand how an ionic bond works, we're going to move on to the focus of the topic, the structure of an ionic compound. This obviously isn't just going to be one ionic bond, it's going to involve many of them to form one big solid. And as you can see in this picture, the structure of ionic solid involves a repeating pattern of positive and negative atoms. Wait, but Galileo, didn't you just say that the charge was zero? While it's true that the net charge of the compound remains zero, the individual ions still carry their charge. Now back to the image, you can see that there's positive and negative atoms because the ions still keep their charge. And one important note about the positive and negative ions. Two positive or two negative ions cannot become too close to each other or else they will repel each other. A really good everyday example of this is table salt. Salt is made of positive sodium ions and negative chlorine ions, arranged in a crystal lattice as we just observed. And the cool part is that when you apply force like hitting or crushing a salt crystal, the layer of ions shift. This shift lines up ions with the same charge next to each other, and since charges repel, the crystal suddenly fractures instead of bending. That's why salt and many ceramics are hard but brittle. And another note, inside of an ionic compound, it's not just repeating ionic bonds, but rather the individual ions form multiple bonds with the surrounding ions. And one last important thing, notice how the positive ions, the cations, are smaller than the anions. These differences in sizes are not just for fun, they're intentional. Okay, then how come a positive ion is smaller than a negative one? To that, I say, you just gotta think about it. An atom's radius is determined by the pull force of the nucleus and the repulsive forces of the electrons. Inside of a cation with fewer electrons, the nucleus still pulls at the same force, but since there's less repulsion, it pulls the electrons closer in. Therefore, the radius is smaller. And as you can predict, it's completely opposite for anions. Since there's more electrons, the repulsive force is greater, therefore they push away further, and the radius is bigger. Now what I said is true if you apply it to a single element. Like of course if calcium has less electrons, its radius would be smaller, and if it had more, it would be bigger. However, if it's different sizes between two different elements, the answer varies. So what I'm trying to say is not all cations are smaller than anions. In reality, it all depends on the number of protons, electrons, and the magnitude of the charge. Now back to the diagrams, this one's a little different because there's way more spacing in between each ion, but the same patterns still apply. You can see that the cation is still smaller than the anion and how there's still a repeating pattern of positive and negative. Now there's another property about ionic solids that we have to discuss, and that would be whether it can conduct electricity. Because you would think that a structure full of positive and negative ions would be able to conduct electricity, right? Well, sadly, this is just not the case, because it depends on the state that it's in. Now open up your ears because what I'm about to tell you is very important. Whether a compound can conduct electricity depends not on the charged particles that it has, but rather if the particles can move. This is exactly why if you melt an ionic solid, it actually can conduct electricity because the positive and negative ions are free to move and carry a charge. This property is very similar to the next topic regarding metallic bonds, where they actually can conduct electricity because their electrons are free to move. But of course, you can see that in the next video. Now finally, we understand this topic, but can we actually apply what we know to practice problems? And I got you. Here's a drawing of the ionic compound, sodium fluoride. Now the question is this the correct way to display the ionic compound? Now you can pause this video to think. But this illustration is obviously wrong. You cannot align the positive and negative ions in this way. Since the sodiums are lined up next to each other, and the same thing with the fluoride, they would both just repel each other. A more stable arrangement would involve sodium being next to fluoride. This way, sodium and fluoride would not be right next to each other, and they would not repulse. Alright, good job. Now let's do another problem. Here's a drawing of magnesium oxide, and I need you to tell me what exactly is wrong with it. Let me just give you a few seconds here. Alright, this arrangement is just plain wrong. Magnesium should not be bigger than oxide because remember, it is a cation, and in general, cations are smaller than anions. And just like that, you have successfully learned topic 2.3 of AP Chemistry. Now if you want to learn topic 2.4, make sure to subscribe and check out the next video. I'll see you in the next one.